Thank you for joining us for this second session of the afternoon here. I'll be talking about the updated camera spatial frequency response for ISO 12233. We've been hearing a lot about 12233, fairly well known of the digital camera standards. And we heard from Ken Parulski, a co-author, about the evolution of this particular standard since the first edition in 2000. And it's approaching its fourth edition, scheduled for issuing completion this year. So we thought it would be good to have a companion presentation on some of the details and the changes in this new edition. First, a few details as a recap for those that perhaps didn't see the first talk. The first edition was issued in 2000, and it introduced an edge-based SFR measurement, a spatial frequency response, largely viewed as a measure of camera resolution or content of image detail, how that is captured and retained. The second edition added two other methods, the sine wave method, so-called SSFR, and that's derived from that target there on the lower right, and then a visual resolution measure, so-called the CPA method. In 2017, there were some minor corrections and revisions, and so it's fair to say this current version has more changes than in the 2017, and some of which were considered but not adopted at that time. I should say my involvement with this standard started in around 2000 when I coded the original edge method. I was familiar with the method, but the original edge gradient method, but then was interested in how it's been adapted for this standard. First, a note on use of the terms. I'll refer to the slanted edge method as it's deriving a spatial frequency response, so-called ESFR. That's how it's referred to in the standard. And for this talk, we can consider that we can interpret the ESFR as a measurement or estimate of the pre-sampled MTF based on the method. I think it's important to define the terms, but not to pick a fight on which term you use. Basic steps are easy to explain, and they're well established. In fact, these basic steps would have been established for edge gradient analysis before we had the standard. We have an edge image, and we acquire a profile that then becomes an effective edge spread function. We take its derivative to derive a measurement of the line spread function. We can do some smoothing, some filtering, and then just compute the discrete Fourier transform, and we end up with the ESFR. It's very easy to describe in these four boxes, but of course the actual steps are more complicated and best understood by reading the standard or looking at the code that's available to follow that. Okay, let me step you through the procedure. We start with a region of interest from an edge feature. The idea is it's a high quality edge, and you can see it displayed there in projection perspective, I should say. That's an actual edge from a scan of a target, and we see evidence of some image noise. The algorithm itself finds the edge and fits it, both the location and its direction. From that two-dimensional matrix of pixel data, we derive an edge function or an edge profile. And in this case, we could think of this as projecting all the data down to, say, the bottom of the array That projection and accumulation we often call binning. So at each of these bins, we accumulate the data. And that's been described earlier in many publications. And how we do that can even be still a subject of research. The basic method is to accumulate them at a sampling interval of 1/4 of the original pixel sampling. Well, after that, we compute the first derivative, or slope, localized slope. And given that the edge vector is a sampled array, we apply a filter. And it's an approximation to an actual first derivative of a continuous function. That's our digital derivative. Following that, we take the discrete Fourier transform by an FFT algorithm, and after some scaling, we end up with the ESFR. The original standard referred to just using a luminance-weighted SFR. Currently, we use the red, green, and blue. And there are many applications of this method, including using it for looking at color registration, looking at measures for limiting resolution, applying single measures like the sampling efficiency, or for example, the 50% SFR point for tracking and quality assurance. In some cases, that would be the KPI for a particular task. All right, well, that's the basic idea. However, with any physical measure, or I guess statistical measure, there are sources of error or variation. So I'm thinking of sort of a statistical view here. So because this method can be broken down into various steps following, we can think of what might limit the accuracy and also the variation or precision. Well, there's the edge fitting. We're finding and fitting the edge location and direction from data, image data that might have image noise, and in some cases, distortion. The image noise itself can add a noise floor. As I was saying before, the signal processing, the discrete derivative, may have an influence on the result. And in some cases, any measurement like this has some built-in assumptions. And when we violate those, we may introduce bias into the measurement. Other types of variation may be due to image position across the imaging field, exposure level, and so forth. Well, that said, let's get to the various steps that are introduced into the updated ISO 12233. The top 1, 2, 3, 4, 5, 6 are the ones that I'll be focused on here. And it's fair to say that several of them contribute to the method being having extended use over a wider range of applications. Specifically, edge angles are no longer officially limited to the near horizontal and vertical. The accommodation of some distortion in lenses where we measure distortion separately from image resolution, and also the smoothing window, which has been adopted, and see how we evaluate that. So that's the outline. So let's proceed. The correction for the derivative filter, it was introduced as an informative annex in 2017, but not part of the main part of the standard. Essentially, the effective line spread function is computed as the first derivative of the edge profile, as I said before. Since this is sample data, discrete pixel locations, or subpixel locations in our case, we compute that with a finite difference here. It's fair to say that if we consider the image as sampled continuous field and the edge profile as sampling a continuous function, then this calculation is a approximation of the equivalent continuous derivative. Fairly easy to analyze, and the derivation is available, I believe, as an annex in the standard. But essentially, we underestimate. This causes an underestimation of the edge SFR, primarily the higher frequencies. I should point out that the range of cycles per pixel, it goes from 0 to 1 in this graph here. Generally, for the image content, we will be looking at a range of 0 to 0.5. That would be the half sampling or Nyquist frequency. So it's fair to say this introduced a modest bias into the calculation. Fair enough. It's fairly easy because it's predictable to understand and also to correct, and we simply divide that out. So that's the first thing that is introduced. Another element that has been introduced is a correction for the edge angle. This was really not necessary to include when the first version of the standard, actually up to now, because the recommendation was to use this approach, this analysis approach, on near horizontal and near vertical edges within approximately 5 degrees. And it worked well. The bias introduced by not including a correction for the edge angle is fairly modest. We can understand why it might be needed by looking at this diagram here. If A and B are two locations from which we're going to project the data, the pixel data, and we're going to do our binning along those lines here, what we see is that in order to derive a profile that is normal to the edge, we really need to accumulate the data or interpret the data as being separated by AC rather than AB. And in fact, as Jackson Rowland talked about in 2015 at this very conference, we see an equation here that really is a scaling one. So scaling of the spatial interval has a corresponding correction in the frequency domain. So in this case, because the scaling of the interval is smaller than the subpixel sampling, we see that it extends the SFR frequency. So a simple scaling there. Accommodating this makes the whole method more robust with respect to the edge angle and tends to support the target, the updated target that Ken was referred to before. That's the correction for the edge angle. About the advanced edge fitting, well, the motivation here was that the original edge SFR method was based on a straight line, a straight, high-quality straight line in the test target, and also a high-quality straight line in the edge feature of the test image. Distorted edge can be introduced by wide field of view cameras, and when that happens in the original method, that introduces a bias error. If you are projecting the data or binning along a straight line, assume straight line of the edge, if you have a curve there, your edge profile will be wider. This will result in your SFR having a negative bias. It will be lower. And there have been various discussions in other standards efforts, for example, in automotive, as to which type of fitting equations you might want to use. The ISO 12233 has adopted polynomial edge fitting, however, has been fairly common practice for some time. And although it wasn't adopted in the previous version of the standard, it's been used in practice and implemented in both commercial software and what I make available in the MATLAB. Our previous speaker, Oliver, was using that, and that was an example where I was commenting that the application of these sorts of methods often extends beyond the current standard method. However, catching up. What are the concerns? Well, how about overfitting? If we have noise introduced, as we often do in many applications, in addition to curved edges, are there problems with the fitting, the higher order fitting? Here's an example where we have an ideal edge which I've corrupted with a fairly high noise and correlated noise, spatially correlated noise, not sort of ever noise. So something that really might have the equivalent noise spectrum that be relatively realistic. And you can see here that because it's ideal, we have fairly good agreement, very good agreement with both the ideal edge and the various polynomial powers. That's a good thing. If we had higher order problems with the fitting of this edge, I would expect to see variations. For example, as we went to 2, 3, 4, maybe the fifth power. Here's an example for barrel distortion introduced into the test target that is part of the new standard. And as we might expect, as we get distortion, we get a reduction in the resulting SFR. So within this small, although small region of interest, if we apply a linear fitting of the edge, it underestimates the SFR that we would get if we went higher. You can see I've done all 5 here, and it's relatively stable, and I guess you could make an argument whether the 4th or 5th would be the best. It's been pointed out, as happens when we're studying these things, that in some cases that the effect of the distortion may be small because your region of interest may be limited, as we have here. With barrel distortion, that's particularly true off-axis, of course. I guess pincushion, it would be larger, but you can reduce the effect of the curvature, maybe reduce the need for polynomial fitting by choosing a smaller region of interest. However, you can end up with problems with windowing bias, overly smooth, and also you reduce the advantage of the line-by-line averaging that you get with the noise reduction. So this is that topic. Another change is the use of a Tukey smoothing window. This turned out, although it was adopted, to have a small effect in most cases, at least for our application. So let's back up. The use of windows is fairly well known, but best known when it's applied for detecting, for example, narrowband signals such as sine waves in a background noise. And often there's a concern about the optimal window for example, leakage, spectral leakage, which is essentially a broadening of the spectrum of the signal that you'd like to detect. However, for our application, an applied window like this really simply introduces a smoothing effect. The window is multiplied. As we see, it multiplies the line spread function, estimated line spread function, and multiplication in one domain is, of course, a smoothing in the frequency domain. And since our objective, the result of this analysis, is in the frequency domain, the spatial frequency response, it applies a smoothing. So we would expect for the Tukey window, which has a parameter here, alpha. For alpha that is a low number, there is a wider window and therefore less smoothing. For the narrower window here, where alpha approaches 1, we see more smoothing. And for reference, I've included the current Hamming window, which is the dotted line here. The thought was that there could be areas near the end of an array that was to be transformed that would have noise that needed to be suppressed. So this Tukey window does go to 0 at the end, but other than that, the general shape is very similar, at least for high alpha. Okay, well, if that were to be true, how about some testing results? This is also a test on both the method and perhaps the implementation one uses. Here's an example on the left-hand side where we're applying the Tukey window for a noise-free known edge. And we see, as we might expect, no real bias introduced by that smoothing function. That's great. This happens to be 44 degrees, something that really works well when we do the correction for the edge angle, the current implementation. And so that's good news. So that's the first step. What about when we add noise? The same edge, when we're adding a fairly high level of noise, correlated noise here with some texture to it, we see, in general, fairly good results regardless, almost regardless of the amount of smoothing, at least beyond an alpha of about 0.6. It's worthwhile then proceeding to look at actual camera images. And here's an example of a Nikon camera with an ISO setting of 10,000. So basically high amplification and pretty noisy image for low light level. And in fact, we do see some smoothing, and you can argue that in this case, as in several others, perhaps the best result was with a Tukey window with an alpha between 0.9 and 1.0. Not too surprising that the original Hamming window would give similar results here. So in summary, we have several areas for which specific changes in the method for the edge SFR reduce measurement variation and aid in the application to a wider range of testing and imaging conditions. For example, the automotive applications and reconnaissance security, for the type of applications that where we're obtaining content from natural scenes, where there's really an interest in finding edges or edge-like features that would be at a range of angles and potentially distortion levels. So in closing, I'd like to say it's been a pleasure to acknowledge the help and helpful discussions and input from many of the other members of this standards group in support of that. I've been working on this with them for about
Thank you, Peter, for the excellent talk.
Yeah. Jonathan Phillips has his hand up, I think.
Yeah.
Hi,
Jonathan.
Hi, Peter. Thanks for the talk. It was good to get the update. I haven't been monitoring the ISO 12233 more recently, and but just in general comments with working with many others and trying to get industry updated to the newer versions instead of the original. The comments come back about the hyperbolic wedge as being something people really look at. From I feel it's really more of a subjective indicator, really more than the objective element of it. So I was curious in the discussions on the committee and elsewhere, the hyperbolic wedge or other visual cues beyond the edge, the straight edge element. Curious what comment or discussion has gone on around that.
Right. I actually have not. I'm sorry to say I haven't really focused on that. I realize that it is widely used, and there have been some discussions regarding changing the shape of it or in order to emphasize, to better sample the various frequencies. And I know Norman Korn has brought that up. So you might want to follow up with him on that.
Sure, yeah, but it is great to see the additional angles being added into the new format. Thank you.
Okay.
Thank you.
Very good.
See, Alex Brown also raised your hand. Do you want to ask your question now?
Yes, please. Hi, Peter again. Well, actually, I have two different questions, but I'll just go with the first one. HDR is, of course, problematic. When you insert a nonlinear function into a linear system, it kind of breaks down. In P2020, Uwe Artmann, of course, is working on that. We basically say, yes, stay within just one linear region. Yeah, but I'd be curious to hear your current newest thoughts, perhaps even wild ideas, how to tackle HDR.
Well, this may be unsatisfying. In many cases, I've thought of this method as evaluating the result, regardless of the processing. So this isn't really, yeah. So I tend to think that since we're doing systems evaluation usually, rather than subsystem modeling, for example, that however it's assembled, as long as you're evaluating the system, the result in the context in it's actually going to be used, then that's how I would normally use these. Now, that said, for example, if there's not a unique, say, tone transfer, that's kind of difficult to go back to exposure. I do appreciate that. But for the actual analysis of, for example, the detailed content, I tend to think of working on the finished file. Am I avoiding your question?
Yeah, absolutely. You are. But I had the exact problem that I couldn't evaluate my camera in the mode it would be used on the road, because I was the knee point. How do I show that? The knee point in the transfer function where you go from, like, say, single digit steps in the noise to 64 steps in the noise to 1024 steps in the noise. And then you would have different noise on the left and the right side of the centroid, and that would, and the worst was if the signal went over the knee point, then it would just blow the MTF out of the water, and that happened in practice. And so I decided, okay, no, we only measure in the morning when the sun is not around the building, so that the level is so light that I'm staying in the first area. But I was wondering about perhaps more modern solutions.
I see. Now I understand. Yes, it's actually interfering with the actual calculations within the IC. Yes, yeah.
It's hard.
It is difficult, and it's probably a longer conversation. I'm going to have to defer to our chairperson.
Okay. Thank you, Alex. I echo your concern. That is a good challenge I also face every day.
It is a hard challenge.
Yeah. Okay. Thank you. Let's give a round of applause to Peter.